Great, thank you. All right. So first of all, thank you for inviting me to this workshop. I think it was a really interesting combination of talks that we heard and really interesting kind of bridge between these different communities that the organizers have set up with the way they put it together. So it's actually really fun, and it was an honor to be here and to be able to talk to you guys. Okay, so I want to talk about something that was. I'm also in a fortunate position because I'm speaking on the last day, so I can refer back to lots of things that other speakers said. I want to talk about higher order graph neural networks, which is actually something that Haggai broached already on the first day, and then it came the slight related ideas, especially as they manifest in terms of equivariance, came up later in the workshop as well. So maybe it's going to be a little bit of a synthesis in this sense. So the plan for the talk is to talk about first talk about why I like graph neural networks. In particular, why it's not really just about graph neural networks, as Bruno mentioned or hinted at in his talk. Really, graph neural networks address, in my view at least, address this a variety of permutation equivariance related problems in a very kind of efficient and powerful way. So, instead of just talking about higher order graph neural networks, I want to give a little bit of a background first, talk about why I like graph neural networks, and then in the second part, I want to talk about what are the shortcomings of this, so why I do not like graph neural networks. This is the broad plan for the talk, and then I'll talk about specific things that we did in our lab to partially address these issues. Okay, so let's start with equivariance. We've seen this diagram before, but in particular, equivariance to permutations. So this is already like a loaded term. So permutation equivariance, if you just use the word on the street, then people will think what you're talking about is that you have a vector, like an n-element vector, and then along comes the permutation group, so the symmetric group, and it permutes the elements of this vector, right? So this, actually, in the machine learning community, is known as the deep sets model, which was first introduced in 2017, and it, in fact, has become very popular, and found a surprising number of applications. Obviously, this is a very simple type of transformation, and also it's fairly clear that the way the permutation group acts on this vector, it's going to have so much opportunity to mix the elements of the vector around that you're not going to be left with the equivariant operations that are terribly powerful or expressive in this case, because compared to the size of the data, the symmetry group is pretty large. So what happens, you can kind of, well, that's part of the story that you can derive this in different ways, but just naively thinking about it, you can immediately see that there are two things that you can do, two types of linear transformations that are obviously equivariant to shuffling around the elements of the vector. One of them is the identity map, or identity map multiplied by some constant, okay? And the other one is just summing all the elements, right? So sum all the elements, and then the broadcast on the other side to all the different slots. You can also do that, and you pick up. So you can do the first one with some coefficient alpha 1, the second one with some coefficient alpha 2, and you end up with these equivariant linear maps with two parameters. So this is what the deep sets paper said, that if you insist on permutation equivariance, then you're left with just two learnable, like a linear maps with just two learnable parameters. That's all that you can do. It's such a strong constraint on your neural network if this is the sort of data that you're facing. Okay, but the permutation equivariance story doesn't end here. There are other actions of the permutation group on other types of objects as well. So for example, you can look at how permutations act on matrices. So they act on matrices by permuting the rows and the columns. Mathematically, this is the formula for it. This is just another action of the permutation group, and then you can ask what are maps that are equivariant to this sort of action. And of course, this is very important to this community in particular, because this is what happens to the adjacency matrix when the permutation group comes along and acts on it. Okay. So let's briefly look at this case. The first thing that is striking is that you have two orbits, right? So when you permute the rows and the columns, what started out on the diagonal stays on the diagonal, and what you started out on the off diagonal remains on the off diagonal. So to some extent, you can treat these two things separately, and you can, again, just by kind of inspection, you can try and find the appropriate linear maps. So regarding the diagonal, it's the same situation as what you had in deep sets, right? So you have the identity map on the diagonal, and then you have the sum, the trace of the matrix, the sum of the entries on the diagonal, broadcast again to the diagonal. So you can do these two things. These are equivariant linear maps. Now for the off diagonal, you have just, again, the identity map. That's fine. But if you think about it a little bit more, then you realize that actually you can take it apart into two different linear maps. So you can symmetrize the matrix, and the symmetric part can go to the symmetric part. But you also look at the antisymmetric part, and the antisymmetric part can go to the antisymmetric part. So you pick up two more independent linear maps that way. And then there's more. So then you can take like row sums and column sums, and you can broadcast them to rows and columns. And finally, you have the overall sum, like the sum of all the entries in the matrix, which again is just a scalar, and you can broadcast to the entire matrix again. So things get a little bit more complicated and messy, and then you realize that it's not just these maps that you can have, but things that behave similarly, that are similar types of objects, for example, scalars, or these vectors that the permutation group, the symmetric group acts on by permutations, or the symmetric and antisymmetric parts. They can also be sent to each other in an equivariant way. So in fact, you're going to have multiple other maps. So the row sums can go to the columns, and the column sums can go to the row sums, and the row sums can go to the diagonal of the matrix, and so on and so on. So these things are a little bit more complex looking, and if you count all this, then you realize that in total you have 15 linear maps in this case. So from the neural net perspective, I mean, that's good. You have some amount of expressibility. You can learn 15 parameters, right? So clearly you can play this game, you can extend this game to the higher order cases. So we looked at vectors and matrices, and next thing, how does the permutation group act on tensors? This is the general formula for kth order tensors, and this does indeed come up potentially in applications. For example, I know Bruno talked about these relational learning. You can have multi-view tables with high dimensions, and I mean, one of the things that I'm going to talk about later in the talk is how this is a natural thing to use in graph neural networks as well to improve their expressibility. Okay, but so this is all good, but how does this all relate to what I talked about at the very beginning of the workshop, which is this representation theoretic, this kind of more principled harmonic analysis view of the same sort of thing, right? So all of these things, like the way that the symmetric group acts on vectors and matrices and tensors and so on, they are just linear actions of the symmetric group. And the symmetric group is a finite group, so everything that I said on Monday applies perfectly. It has irreducible representations, which you can enumerate. There's a finite number of them, they're finite dimensionals, and any representation breaks down into a direct sum of irreducible representations. So why can't we do it that way? What would that approach to this sort of problem of finding the linear equivariant maps actually give us? Okay? So this is with I remember that we actually had this on Monday. So what are the representations of the symmetric group? Well, here is one representation. It's the permutation matrices themselves, right? So some people think that the symmetric group is the set of permutation matrices. I mean, it's kind of true, but it's just a more abstract way of thinking about the same thing. But certainly, the permutation matrices do multiply the same way as the corresponding permutations do. So that's fine. That's a representation. But the kind of nasty surprise right at the beginning is that this is already not irreducible. Okay? So in particular, it's not irreducible because if you think about these permutation matrices, they're stochastic matrices. So if you take the all one vector, then that's preserved under the action of all the permutation matrices. So you have a one-dimensional fixed subspace. So there is a one-dimensional representation lurking inside the permutation representation. That happens to be just the identity representation. And then you have this n-dimensional, n-1 dimensional part left, which actually turns out to be an irreducible representation. But already this kind of defining representation of the symmetric group is not irreducible. So you need to be a little bit more careful, and then all these questions come up so what are the irreducible representation of the symmetric group then, right? How big are they, and how do you compute them? And if you take the actual representation corresponding to how the group acts on, say, tensors, then what sequence of irreducible representations does that break down to? So this is a super fun subject, and I'm not going to spend the rest of the talk talking about it, but I just want to give you a sense for it. Maybe it's going to be useful, or it can be useful, at least it gives a nice kind of complementary perspective to things that we are already doing in this graph learning or permutation equivariant learning community. So the first interesting thing is that these irreducible representations are not indexed by, say, numbers, but by these little diagrams. So what happens is that if you're looking at the permutation group over n letters, then you form diagrams like this, consisting of n boxes. The rule is that no row can be longer than the row above it. So this is a valid diagram for S10, I believe, because there are 10 boxes in total, right? But you can imagine that you can do this in many other ways. You can lay down these diagrams in many other ways. And each diagram is going to have a corresponding irreducible representation. So that's just the weird mathematics of this subject. Okay, now the next question is, okay, so we have these, like we know that we're going to have these irreducible representations, but how big are they, right? So on Monday, we talked about the irreducible representations of the Lie groups, so SO3 and O3, and those representations were indexed by just integers, and say the irreducible representations were always a dimension at 2L plus 1. So it's a nice sequence of like increasing matrices as you go down this sequence of irreducible representations. So what about the symmetric group? Okay, so okay, this is what I understand. So for that, you need to go back to your diagrams and do something else. You need to stick numbers in them. So you put the numbers 1 to n in this diagram consisting of n boxes. There's an additional rule that you put them in such that in each row the numbers increase from left to right and each column from top to bottom. So there's a certain number of ways that you can do this. Any such filling of the diagram with the numbers is called a standard Young tableau. And then the assertion is that for a given irreducible representation corresponding to a given diagram, there are as many, the number of dimensions is the number of ways in which you can do this filling. In particular, it's because these diagrams, these funny things with the numbers in them, actually going to correspond to the rows and the columns. I'm not going to talk about like the third and the fifth row or column of these matrices. I'm going to talk about the row or column corresponding to this particular Young tableau. Okay, so I know it's weird. That's why I like it. And there is a lot of, this is not new. This was worked out 120 years ago. And there's deep reasons why these kind of combinatorial objects should even appear here. And it's not at all apparent what this directly has to do with graphs and then the start. And it turns out that the next question you ask is, okay, so I've got these weird irreducible representations. I know that they have these weird sizes. Actually, the size increases pretty drastically. Maybe it's on the next slide. But what are the extra elements? It turns out that that's also something that you compute from the way that you put these numbers in the diagrams. So I'm not going to spend too much time on that, but you can believe me that once you take this view of looking at the matrices in terms of the standard Young tableau, and you look at, for example, adjacent permutations, adjacent transpositions, or transpositions to just swap I with I plus 1, then the corresponding matrix is going to be very simple, and the non-zero entries are given by this formula. Okay, so it's an orthogonal representation. Don't look at it for too long. But from a computational point of view, actually, what's important is that it's actually very sparse as well. So these representation matrices are sparse, and so this is a really beautiful theory. It has surprising connections to various things. For example, people in more on the statistics side have explored how you can use these irreducible representations directly to characterize kind of projections of distributions over the symmetric group to particular kind of marginals. So there is kind of some order to this weird theory. The first irreducible representation kind of gives you the overall mean over your data set. The next one is gives on top of that gives you information of like what is the like average cost or average utility of mapping the ith item to the jth position. The next one is what if I map I and j together to k and l. The other one is the same thing, but not as sets, but as vectors. So it's the ordered version of this. And there's this whole sequence of like peeling away more and more information from your distribution or your function over permutations. As you look at kind of these higher irreducible representations. So the whole atmosphere of this, it's a generalization of Fourier analysis, right? So you've got information on a complicated object, and you've got a systematic way of extracting information at increasing levels of complexity. And at the same time, because these irreducible representations and general theory of equivariance and so on, it's also a prescription for how to get the equivariant maps. Okay. So moreover, this is more. It turns out that this system also, this kind of Fourier analysis also has a very strong computational side. In particular, people have come up with fast Fourier transforms for signals on the symmetric group, which work on this kind of recursive partitioning idea that you take the symmetric group over n letters and you find n copies of the symmetric group of n minus 1 letters in it, and each one of these n minus 2, and relate all these bigger Fourier transforms to the smaller ones. That also means relating the irreducible representations to each other, but the irreducible representations kind of nest inside each other in a very natural way, related to, again, the diagrams. So you can do it very efficiently. So there's been this little kind of cottage industry of devising fast Fourier transforms for different finite groups, and the symmetric group case was maybe the first real major result here, and kind of the paradigmatic case in the late 80s by Clausen. There were many variations on that, and it reduces the cost of taking this decomposition, so taking a function on all permutations, decomposing it into irreducible representations from n factorial squared to order just n cubed times n factorial. So depending on how you look at it, this is either amazing. This is just like the ordinary fast Fourier transform, going from n squared to n log n is the same sort of thing. Or, I mean, come on, there's an n factorial there. Seriously talking about doing this, right? So However, that's actually not the right way to look at all this theory, I think. And the right way to look at it is that is to focus on exactly this diagram and how these irreducible representations are related to each other, and realize that most of the time you never even have anything that's on the full symmetry group. So when you want to apply this theory to, say, computing equivariant maps between kth order tensors, then all the data actually only appears in the corner of this diagram, that you get by going from, going down k levels, so from the full group to the n-1, blah, blah, up to n-k, and then looking at this irreducible representation of this Fourier component and all the other components that are descendants on this, so like these guys, okay? And these are going to be the components that actually show up. Everything else here in the diagram is going to be 0. So it's actually not that bad. And in polynomial time, you can do all these things. You can take the tensor and compute, compute its Fourier transform, so the projection onto all the irreducible representations that actually show up. Then you can do the linear map in that space, and then you can go back, and it's a viable algorithm for, say, this kind of higher order equivariance problem that we actually see in higher order graph neural networks, in hypergraph neural networks, and so on and so on. So is this the way that people actually do it, or is this the way that we should actually do it? No. So there is another way to do it, and there is at least one person in the audience who's very familiar with it, because he's the high guy, because he's the one who wrote the paper on this 6 years ago now, which is to say that, okay, we want equivariant maps between k1th order tensors to k2th order tensors, and we can then how do we enumerate them, and how many of them are there, and what are they actually? So, for example, take the case of k1 equals 2 and k2 equals 2, so going from matrices to matrices, all the equivariant maps, then actually you can form a basis for these maps just by considering these really simple linear algebra expressions. So, for example, you sum over both indices here, and then you broadcast. Or you sum just over the diagonal, and you broadcast. So these are exactly these are 15 of these in the 2 case. These are exactly the 15 maps that I mentioned earlier, which you kind of could have arrived at by inspection, but at some point you probably would have gotten a little bit, you would have made a mistake, because it's a little bit confusing at a certain point. But actually, there is a system to this. These are basically the possible Einsum expressions going from a matrix to another matrix, right? So these operations, they look like this, right? So you have an input tensor, which is some number of indices, and then you select a subset of the indices. First of all, you can tie indices together, right? So if you tie indices together, that just means that you're looking at the diagonal. And if you look at some of these tied indices and you sum over them, then that's like a contraction over those indices. If you do not sum over them, then just says that you are on the diagonal in that case. And then you compute this expression and send it over to the other side. And there again, the question is how the indices from the left-hand side match up with the indices from the right-hand side. So enumerating this so it's like listing them out like that might be a little bit kind of overwhelming, but really this is just the number of Einsum expressions going from k1th order matrices to k2th orders in the indices. In the original paper, the result was framed in terms of just the size of this basis, so the number of such independent linear maps, independent equivariant linear maps that you can have, and the result was us that this is actually given by the Bell number, so the number of possible partitions of the set 1 to k1 plus k2. So if you look at it in terms of Einstein expressions, or look at it in terms of these indices, this is not at all surprising, because you really are just partitioning the indices of these matrices, right? Or tensors, right? So let me sketch on the board. So I don't know, like you have I1 blah 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 up to IK1 on the input side, and you have J1 up to JK2 on the output side. Okay, so this is then. The first question is like which indices are tied together. So you kind of draw this, like maybe this one is tied together with this one and this one. So there's one partition there, and there's another one here, tying these two together. And there's a third partition which actually ties some indices together from the left-hand side to the right-hand side. So maybe it's going to be like this. Okay. Okay. So the nature of these indices is different, because this one only includes indices from the right-hand side. So that means that in terms of the operations, you can be summing over them. This one only includes indices from the left-hand side. So that means that it's going to give you directions or diagonals that you broadcast over. The third one involves matrix indices from both the left and the right. So this is what I would call transfer indices. But all this doesn't matter. This is just the entire expression, the entire linear map is just determined by this partitioning of the indices of the jointly the input and the output. So there are as many such linear maps as there are ways to partition the numbers 1 to k1 plus k2. That's exactly why the Bell number appears here. Okay, so this is the same thing, right? This is an equivalent. This is a equivalent basis to the basis that you would get with the fancy representation theory, but I mean, there are many of these maps, but still they're kind of easier to implement actually in the software. But it's interesting to have this kind of dual perspective on permutation equivariance. Okay, so the next thing is this is all good, and now we know how to do permutation equivariance in neural networks. And we know that for graph neural networks, the fundamental criteria is that they need to be equivariant to permutations of the vertices. But I'm also telling you that, and this is actually something that jives with Soledad's talk from, I think, yesterday, right? That there's only a fixed number of these maps, and the fixed number depends on just the order of the input and the output. It doesn't depend on n. She said this explicitly as well. So is this going to be a good way of building equivariant neural networks? Am I telling you that if you want to have a graph neural network for graphs of, I don't know, around 30 vertices, then you are going to be looking at these 30 element vectors, or 30 by 30 matrices, or 30 by 30 by 30 tensors, or worse, and then you are going to be just enumerating all these kind of combinatorial number of linear maps and applying the same linear maps independently of how many vertices there actually are. So there are multiple ways in which maybe this is not the ideal thing to do. For example, when you try to apply this to a social network graph, and I'm telling you that you need to have a 10 million by 10 million by 10 million tensor, it's probably, and do harmonic analysis on that, it's probably not the best way. This leads to the realization that we talk about permutation equivariance, and in some sense, that's actually what really drives the entire field. But the actual graph neural networks that we have are invariant, but not to the same group, so not to the full symmetry group. Because what you really want is permutation equivariance to just the automorphism group of the actual graph that you're looking at. right? And this is again something that was mentioned today already, but maybe a couple of times before in the workshop. That why do we care about equivariance in the first place? So I like to think about equivariance in terms of this little pixie that comes along and messes up your learning algorithm for you, right? So you've learned a lot of stuff about a certain graph or a certain class of graphs, and then the little pixie comes along and presents to you another graph which looks just like the original graph, but he kind of messed up the ordering, right? To change the ordering of the vertices. And now your task is to defend yourself against these pixies and still be able to recognize that it really is the same graph or the same sort of graph that you had before. So there's a real danger of this happening when your graph has symmetries and the ordering of the vertices is permuted according to something that is in the symmetry group, in the automorphism group of the graph. But if it's not in the automorphism group, so it's some other type of permutation, right? So you have a graph where you've got an edge hanging off one side or a really central node, then as soon as you see the graph, it's obvious what node that is, right? So I wouldn't actually need to worry about that node being confused with any other node. So it's not the full symmetry group that you really should worry about. It's the automorphism group that you care about. So this seemingly makes the situation much harder, right? Because a large graph can have a really complicated automorphism group. I believe it's NP hard to find the automorphism group. And then I'm telling you that you need to find the irreducible representations of this weird group and do some manipulations with that, blah, blah. It seems a little bit daunting, right? But in reality, this is what message passing neural networks actually do. And they do it by a trick. The trick is that so this is the automorphism group. So the way I like to think about message passing neural networks is that they are not equivariant to the entire symmetry group by themselves. They're equivariant by nature of the fact that they kind of drag along the adjacency matrix and use the adjacency matrix as side information to restrict the kind of symmetries that you need to incorporate in the first place, right? So in the message passing neural network, every layer is determined by the adjacency matrix. So if the layers actually explicitly see the adjacency matrix, and they use that information to allow a relatively large set of possible equivariant operations, which are still equivariant to that adjacency matrix, but wouldn't be equivariant if you were allowed to arbitrarily permute all the vertices of the graph. Okay, so it's like dragging along. At each layer, the neural network sees both the activations, which is something related to the vertices, and the adjacency matrix. And the activations in the adjacency matrix can both be permuted by the group, but they're permuted in the same way. So the adjacency matrix is a huge clue as to what actually happened, or what the pixie might have done to the activations. Yeah.
A quick question about how do you say computing the automorphism group is NP hard? What do you mean by that? What is the representation of that group? Is it the generators of that group?
Yeah, so right. So I suppose that's how you would do it. So you would need the generators and the relationships between the generators. Like nobody in his right mind would do that, right? For actual graph neural networks. Yeah.
There are tools to do that.
Yeah. Yes?
I asked this question also to solve that. So isn't this automorphism group too strong for the message passing? Because you know that they cannot detect, differentiate between, like non-isomorphism classes and so on. So it's that there's a much weaker kind of invariance that is actually sufficient for graph learning. Right?
Yeah, so the message passing manages to, this was in the category of why I like graph neural networks, right? So it manages to do something that's equivariant to the automorphism group without explicitly finding what the automorphism group is. And I think that's kind of clever.
No, sure, but it actually does less, right?
It wouldn't be able to tell you what the automorphism group is. So you explicitly ask for it, it wouldn't be able to do that, yeah.
So when you're looking at the specific groups on which you want to be invariant, you want actually to have like the equivalence relation that is actually upper bounding the power of the graph model, no?
Mm-hmm. Yeah, possibly. Yeah. All right. So let's get on to the second part. So after having advertised how graph neural networks can kind of cut through this algebraic complexity, what is it that they cannot do? So what is it that I do not like about graph neural networks? In particular, graph neural networks have almost become synonymous with message passing neural networks. And as we know, I mean, this is the kind of paradigmatic case. There are lots of times that this was kind of discovered and rediscovered in the literature. What happens is that vertices collect information from their neighbors, aggregate the information, and then do some internal processing. But the key thing is that the aggregation is in the form of the sum, like the sum of the messages from all the neighbors. And summation is an associative and commutative operation. So that's the key. So it can be replaced by something else. So for example, Yusu talked about these kind of max type graph neural networks. That's fine because that's also an associative and commutative operation. But I mean, the reason that this whole process is ultimately going to give you something that's equivariant to relabeling the graph is because you're using an operation here, which is associative and commutative. But doing this also means that you are really kind of impoverishing what kind of relations you can learn. So saying that you push everything through, say, summation means that as soon as you've done that, you've forgotten where the information came from, right? So these neural networks are often called graph convolutional neural networks because of this analogy with classical convolutional networks and images. But it's a little bit of it also, sure, it's a local operation. It's a bit like convolution in some sense, but it's like convolution with filters that don't know the difference between up and down and left and right. Right? So that's, to me, this has been bothering me from the start, right? That you combine information, but in such a way that, I mean, clearly you care about like how it relates to the underlying graph and what came from where, but you immediately forget about it. At every single layer, you do this kind of forgetting for the sake of having equivariance. And this is the reason that these algorithms are like one vice for the lemon, and that's why they're also their expressive power is limited similarly. Okay, so if you take a step back, then message passing graph neural networks are not the only type of neural networks that people have thought about. Actually, around the same time, or even maybe before by some historians, people have come up with another idea, which is to use the eigenvectors, right? So again, this all comes from this equivariance point of view, right? It seems really daunting to come up with an algorithm which just cares about the graph, but is equivariant to the ordering. And maybe the first idea that comes to mind is, okay, let's just do something in terms of the eigenvalues and eigenvectors of the graph, because as long as you can neatly like order the eigenvectors, then they are going to be equivariant, right? That's not going to depend on how the rows and the columns of the matrix have been ordered. Again, Bruno talked about this and the limitations of this, and he has this clever trick of getting around the potential problems with this. But anyway, so this is really classical. Going back in the graph learning literature, even before neural networks, is to get around the equivariance problem by this kind of spectral ideas. And then there's the other kind of approaches, the message passing approaches, where instead you do these local operations with the aggregation. And in my mind, these are kind of at the opposite ends of a spectrum, because the spectral approaches are great because there's a long line of literature saying that they really allows you to discover and leverage the global structure of the graph, right? Whether the graph is more like a elongated thing, like a single path or a tree, or it's more like a ball, that really is is kind of apparent from the eigenvalues. The eigenvectors are natural coordinate, at least the first few, natural coordinate systems for graphs, which have this kind of geometrical structure. So you can hope to leverage a whole lot from that side and get an algorithm which has a kind of firm grasp of how overall what the graph looks like. What it's really bad at is capturing the local information. And that's because these eigenvectors are typically dense over the entire graph. And then they become very kind of close to each other, and there's numerical issues and stability and so on. So this sort of thing is good for finding the global picture, but not good at answering questions like, okay, how many functional groups of a particular type does this molecule have? Or how many isolated vertices there are, that sort of thing, okay? The message passing neural networks are at the opposite end because they only do local operations. That's another kind of dirty secret of this area, that often when we do message passing neural networks, we only really do it for like 3 or 4 or 5 or 6 rounds of iterations. So this algorithm doesn't even see the entire graph, right? It only sees stuff in this ball of radius 3 or 4 or 5 or 6, and then you do this thing of you aggregating, which is essentially like counting. So these message passing neural networks are a bit more like counting the local features, just identifying local features and then counting them. And there's this whole bunch of stuff, at least conceptually, in between that is missing. So, I worked at the Flatiron as well, so I'm indoctrinated like in multiscale algorithms and fast multiple and so on. So whenever you look at objects in nature with complex structure, the kind of the natural thing is to break it down into constituent parts, see how the constituent parts relate to each other and form larger parts, and how the object looks like at the level of like the individual little bits, and the kind of conceptually more complex larger bits, and how the whole thing fits together into one object on the top. So ideally what we want to do is to have graph learning algorithms which can do this, which can actually build up this hierarchy and access all the intermediate levels as well. It's really difficult. So there are specific reasons why. There are attempts, but it's been very difficult to come up with a efficient and practically powerful and mathematically consistent way of actually building a multiscale hierarchy of graphs, because graphs are like these like loosely ordered objects, right? So it's not just like a Euclidean space where you can relatively easily build these trees. Okay. All right, so that's like my second complaint about graph neural networks, kind of this glaring thing. It also relates to, again, to some of the other talks, like the optimization, right? So this question was asked that if you want to use the graph neural network to guide one of these branch and bound algorithms, then what can you hope from a graph neural network that at the end of the day only looks at just local operations? Obviously, the whole point of what's difficult about optimization problems is when there's a kind of global issue that you have to address, but it doesn't like immediately jump out from you from the local operations. So it'd be great to have something that can capture things that at multiple different levels of resolution. Okay. All right, third complaint. So you can see that my kind of grudges are kind of piling up. So message passing neural networks are really clever, but what they really do is that they pass on the problem of capturing the topology to the compute graph, right? So this is again from the first day. Every neural network has a compute graph, and it can get pretty complicated. And what graph neural networks say is that we're actually not going to try and use some sophisticated graph theoretic approach to actually addressing topology. We're just going to build an algorithm whose compute graph is determined by the topology, and hope that in this process, like the fact that we implicitly encoded the structure of the graph in the compute graph, the behavior of the compute graph is going to reflect the behavior of the nature of the underlying graph. Okay, so it's like an interesting and slightly weird trick. Okay. All right, so the fourth and hopefully last complaint is that sometimes you know what convolution is supposed to look like. So if your graph has, say, cycles, which many graphs often do, and sometimes they are very well identifiable and they're critical, like in molecules you have these 5 cycles and 6 cycles, then you know what convolution is like on the cycle or on the cyclic group of order n, right? Or there are paths. And then again, you can, with classical methods, you can describe what convolution is there. So if we have a graph neural network which is supposedly doing convolution in a graph consisting of these elements, then why doesn't that convolution reduce to these classical notions of convolution in the limit? And it doesn't. Okay. So again, there's somehow a little bit of graph. So related to all of this is that I think when we talk about graph neural networks and graphs, all these different people actually have something different in their mind. So it's a massively overloaded term, right? So this is a theoretical computer science directed workshop. So for theoretical computer scientists, a graph is this combinatorial object, right? It's all about like exactly where the edges are, and when there are no edges and 2 graphs you just perturb, one edge is completely different and you want to distinguish between all graphs and so on and so on. So that's one view of graphs, okay? Another one is like a network, right? So sure, a network is a graph in some sense, but when you're talking about the social network or Quora or something like that, then you don't care about like identifiability and distinguishing between one social network and another social network. You're much more looking at like global properties or some underlying order in the thing. And also the size is completely different. Yes? Yeah, I can try and look it up. I'm not sure exactly off the top of my head. I'm sure that people have looked at it. Maybe some people in the audience know more about it. It doesn't.
So I think like the Gunnemann group has a couple of papers where they kind of combine spectral and like global local methods. Also, if you use virtual nodes, it has a close relationship actually to mixing spectral and local methods. I can send you some.
Okay, thank you.
All right. Okay. So networks are types of graphs as well, but really the emphasis in a different place, the thing that we focus on, or the way we even think about the graph is quite different. Now, there's molecules, which more like small molecules look like small kind of combinatorial graphs. But again, there are these distinguishing features. So for example, it's a planar graph, right? In R2 or R3, it's usually embeddable. And it usually has just particular features. And you really care about counting individual type of substructures called functional nodes. And incidentally, the whole thing is a fiction because there is no, like a graph of a molecule is just a way of us conceptualizing how the electron orbits more or less look. But the nature doesn't know about the underlying graph. Nature only cares about the wave function, and it's already a pretty kind of rough approximation to think about a molecule as a graph. Okay. Now the third one, or the fourth alternative, is when people use graph neural networks. They say that these graph neural networks to build neural networks for, say, learning force fields, right? Where this is again something that the geometric graphs that came up on the first day as well. Hannah talked about it and so on. So there the situation is that you're trying to capture some geometric arrangement of a number of particles, and you have some notion or some guess that the interactions that guide the system are to some extent local. So there's a nature of neighborhoods, and it's natural to build up algorithms that iteratively collect information or process information within those neighborhoods. So sure, the neighborhoods define an underlying graph, and this is why people use the word like equivariant graph neural networks for this field. But it's actually very different to say the combinatorial object part, right? You're not looking at individual little patterns in these graphs. All that you're really saying is that not everybody communicates with everybody. So then you need a way of capturing like who is connected, like who needs to communicate with who, and that's captured by a graph. But that's more like a graph in the sense of, a sparse matrix is a graph, right? Sparse matrix multiplication is a graph operation. Okay, then there in graphics and so on, there's meshes. meshes, which is again graphs with very special properties. There is relational graphs, which is kind of fascinating, and the permutation equivariance really comes into play. This is partly what Bruno talked about. And finally, graphs are often used, especially in more applied domains where people don't know what they're dealing with, right? So when you've got data and, I don't know, like interactions between things in a cell, and you really want to leverage what's in the literature, so people wrote papers about how A interacts with B and A interacts with C, but they didn't write a paper about B interacting with C. Well, maybe it's because they do not interact, or maybe because nobody bothered to write the paper. But anyway, you can think of it as a graph. So if you insist on putting that sort of information into a learning algorithm, then the natural thing to reach for is a graph. But it's not the same as, I don't know, using like solving graph isomorphism. The emphasis is in a totally different place. All right. So this is great. I told you all my biases, and I've got 8 minutes to start to talk about some more original work left in the talk. Okay. So to address some of these obvious limitations of the original message passing paradigm, a natural direction to look at is to look at still message passing, but message passing between larger substructures, right? So in particular, message passing between subgraphs. This is again something that Haggai mentioned, I think, on the first day. And there are multiple different perspectives on this. One of them is really just subgraphs and information exchange between subgraphs. The other one is to talk about hypergraphs, which a hypergraph is really just like identifying these higher order structures they can all flatten it into a graph, or even simplicial complexes which are hypergraphs with kind of particular constraints. But it's the same sort of idea. So what if you have this collection of objects and you don't just have binary relationships between them, but you have subsets of the objects on which you induce like higher order relationships, and then these also need to communicate with each other in an equivariant way. Okay. So again, this is something that is, I mean, if you look at these chemistry or biophysics type of problems long enough, it kind of screams at you, right? So you've got molecules like this, and sure, you can think about it in terms of the individual carbon atoms sending information to other carbon atoms, but it's not really the individual carbon atoms. I mean, these carbon atoms really have shared electron orbits and so on. It's really one unit. So you should think about it as a single entity and communicating with another entity. But then these questions come up, but of how do I do it in such a way that I don't lose expressive power, so I can still identify, which vertex of what happens at which vertex of this benzene ring versus that benzene ring, and how should they communicate. So there is this hierarchy of subgraph neural networks of different orders. So for example, you can have the first order subgraph neural networks where each subgraph maintains an activation which is on which the symmetric group or the local symmetric group acts by its first action. So like the first element here corresponds to one carbon atom, the second to the other carbon atom, and so on and so on. Or you can look at the second order case where you have matrices, right? So that can maybe in some sense capture relationships between the internal constituents of these subgraphs as well. Or you can look at higher order things as well. And then the interesting part comes in when you think about how should message passing work between these higher order structures, right? So when you pass information from one ring to another, you realize that you need to somehow treat parts of the information that relate to the shared vertices differently to the ones that are not shared in order to satisfy equivariance, but at the same time be as expressive as possible. So you need to identify the joint vertices and potentially do something different there. For the second and higher order cases, it gets even more interesting, right? Because you need to identify shared elements and shared rows and shared columns and shared slices and so on and so on. So what are the rules for equivariant message passing in this case, where there are all these different tensors partially overlapping with each other in your graph, and you need to figure out how they should communicate? So this is what our work, which was published last year, addressed. So what we kind of realized was that you can develop a mathematical theory for this, but it quickly becomes pretty unwieldy and confusing. So we felt like we needed to introduce a new abstraction which kind of captures all the mess and allows you to talk about these things at a higher level, and also to program them, right? To have software which can and instantiate all the possible linear maps without diving into the messy details of exactly how the different how these different subgraphs overlap. So we define this concept called a P-tensor, which is this generalized permutation equivariant tensor, which transforms the correct way according to the action of the local symmetry group. It's a terrible name. Apparently, P-tensors is already well established in statistics and means something different, but I apologize for that. Yeah?
What is the relation between these atoms, these x1 to the rest of the definition?
Yeah, so these are the vertices, right? So we call them atoms, but not just necessarily chemical atoms, but atoms. So they are the individual things that index the rows and the columns of these tensors, right? So we try to formulate it in such a way that it corresponds to graphs, but not just graphs. It can also be used for some kind of relation learning thing as well. So you've got a universe of atoms, and you've got these little vectors or tables relating to subsets of those atoms, and then what is the way for them to equivariantly communicate. Okay. All right. Yes.
So the atoms, how does it show up on the P-tensor? Or is the P-tensor the transformation acting on the atoms?
That the first dimension of the P-tensor corresponds to the first atom, the second, or like the first row or column, blah, blah, blah. So it corresponds to the first atom, the second one to the second atom, and so on, and so on, and so on. So these are the atoms, and these are the i's are the corresponding numerical indices. Yeah. Okay. All right. So I really need to hurry up. So the situation is that you've got all these different objects, and they're kind of well defined, and the transformations between them are well defined. You just have to say what are the underlying atoms. But it's seemingly like creating equivariant maps between them is a little bit daunting. But then we come back to this to Hagai's work about equivariant maps within tensors and Einstein connection and so on. So if you think about it. In reality, there's a natural way to extend those kind of linear maps that appear when you are mapping from a k1th order tensor to a k2th order tensor in its entirety to doing this mapping when the indices or the dimensions of the tensors only partially overlap. Okay, so. Basically, the rule is that for those dimensions that occur in both atoms that occur in both the input and the output, you have the regular maps that you've always had. But what you need to worry about is those indices that you either do just the contractions over, or that you do the broadcasting operation over on the other side. So this is captured. So I'm talking about these partitions of order P1, P2, P3, where P1 is the number of contractions on the right-hand side, P2 is the number of transfer indices, and P3 is the number of broadcast steps on the right-hand side. So for these two types, for the contractions and for the broadcast types, every time you do one of these operations, you basically have this choice of whether you just contract or you broadcast over just the joint indices or all the indices of the input versus respectively the output tensor. Okay, so there are going to be more equivariant maps than if because of this partial overlapping issue, and the number of excess maps is just going to be like for each each potential partition, you have not just 1, but 2 to the p1 plus p3 possibilities. So the number of possible maps between these partially overlapping p-tensors grows even more steeply than in the original case. Okay. But it's still the same sort of operations. We didn't do a very good job at writing this down in the paper, but it's a relatively simple proof. What remains is to make this stuff kind of usable. So maybe, yeah, in the remaining non-existent time, or yeah, I'll just talk a little, just say a little bit about that. So one thing that we realized is that the vast majority of people in the field use a specific software package for research on graph neural networks, and that's PyTorch Geometric. So PyTorch Geometric offers you all sorts of things, but at the core of it, it gives you two kind of functionality which is difficult to replace. One of them is just these gather and scatter operations on the GPU, right? So what happens in the message passing neural network is that every vertex needs to collect information from its neighbors. So you need to pump all the information into one spot, and you need to do this in parallel for all the vertices of your graph at the same time. And there's potentially a write conflict, right? Because you're pushing multiple bits of information into the same spot. So you can't just, so it's like a sparse matrix product operation. So PyTorch Geometric does that with it by kind of using the underlying gather and scatter operations from PyTorch itself, and it's relatively efficient. It's actually not, but not necessarily the best that you could do. It essentially uses mutexes to avoid the write conflict. The other thing is that in order to get the best out of your GPUs, you need to pump a sufficient amount of computation onto the GPU at any moment. So people use batching, and there was this realization that in this message passing framework, batching is relatively easy to do simply by taking all your graphs in a given batch and merging them into a single disconnected graph and pretending that it's a single graph, and then just at the very end maybe taking it apart, right? So batching, the way that matching is done in PyTorch Geometric, is in this trivial way of just combining everything into one big graph. This, by the way, this diagram is what I got from ChatGPT-5 when I asked it to illustrate this. I don't think it did a particularly good job. It's way overcomplicated, but never mind. So so this is good. This is the actual code in PyTorch. This is the scatter operation. You can see that this write conflict is solved with this atomic compare and swap operation. It's a little bit weird because, and you might not know this, but actually the way it is done is that it takes out the old value, adds the increment to it, and then tries to write it back as long as where it's writing has not changed in the interim. If it doesn't, then it tries again. So it's actually a loop that waits on all the other threads until the operation is possible. And that's not necessarily, I mean, this is the question of if you really want to do this at scale, but this is an optimal way of solving this this write conflict problem. But anyway, so the problem is that this is fine for regular message passing neural networks and various tweaks that can be done on top of it, but it doesn't naturally apply to this higher order message passing that we want to do. It was really clumsy to put it into PyTorch Geometric. So we ended up writing our own library, which has individual CUDA kernels for the specific types of reductions and broadcast operations that come up in these higher order networks. And the intent is to use it both for graph neural networks and for other kind of permutation equivariant problems where the same sort of maps appear. And the interface should be very simple and kind of hide all the details on the back end. So really what happens is that you just specify that you want to have a first order P-tensor over these atoms, okay, or 2 P-tensors over this pair of atoms and that pair of atoms, and then you specify the other P-tensors, and then you say, okay, now do message passing in all possible ways between all these P-tensors, and all the magic happens on the back end without you having to worry about exactly how it's translated to the GPU. All right, so I think my time is up, right? I wanted to, there's a third part of the story. Let me just describe it at the high level so that you can ask me later, maybe, is that we came back to this whole issue of message passing between subgraphs and what happens in the subgraphs and so on, and in particular, that, okay, we want to instantiate this on, say, molecules, and the natural thing to focus on are again, the little paths and the little cycles. And then again, that our model is now back to the same situation that locally, in terms of little cycle, it assumes full permutation equivariance. So how do we get around that? And we have an approach which is weird because it goes back to the spectral way of looking at it. It's again like we don't want to enumerate the automorphism group of the local subgraphs fully. So why don't we do something spectral? And we discovered that in some sense, the spectral is almost as powerful as the best you could do with the actual group theory. So maybe what I started with in terms of this contrast between the spectral and the message passing neural networks and how spectral neural networks are limited in some way and they don't fully capture all the algebra, maybe that's a little bit unfair. Because if you could actually exactly do the spectral approach, it would, in the kind of harmonic analysis that it suggests is very similar to the algebraic approach with the group theory. All right, sorry for running a couple minutes over time. All right, not sure where to.
Questions?
Yeah. Yes.
Yeah, just a quick comment because we are assignments and I don't want to be overly pedantic, but computing the automorphism group of a graph is not NP-hard. I mean, this is equivalent to the graph isomorphism problem.
Oh, okay. Sorry.
That's also why I asked. So, right. So if you want to compute the generators of the group,
yes.
Then yes, what you just said, right?
Okay.
Exactly, but yeah.
Yeah, sorry about. But
yeah, no, that was.
I've seen it in the literature multiple times, so just.
I see. Yeah. And it's easy to see why the two should be related, right? Because if you put two graphs together and you find the isomorphism, you find that the symmetry that takes one graph to the other is in the automorphism group, then the two graphs are isomorphic.
There are also actually quite, so for smaller graphs, tools that could probably do it actually quite efficiently. Yeah, so Naughty and Saucy and these types of tools exist.
Yeah?
Thank you for a very nice talk. I really like the picture of you're asking what is a graph.
Yeah.
So can you remark on, well, we heard some talks about graph foundation model or towards graph foundation model. And do you think that based on these very different natures of the graph, like if we want to go towards graph foundation model, is there any hope, or you need to like specialize one model for a class of graph? Or you can reduce it to a more modular computation that maybe it can work for.
Right, so that's a possible criticism of graph foundation models, or not graph foundation models as a whole, but saying that why don't you just, like if you're interested in molecules, why don't you just build a foundation model for molecules? If you're interested in large networks, why don't you focus on that? And then there's this like the philosophical question of like, what happened with large language models, right? So the original idea in large language models is that I take all the information of the internet and I just teach this thing to speak English. And then later on, if I want to prompt it in English to do other things, then obviously it helps that it has learned English already. So building a foundation model for English, or this kind of concepts that people talk about in English, is a good idea. But there too, like there are these observations that learning English helps with learning learning to code, and vice versa. So maybe there are surprises like that with graphs as well. So I don't know. Like maybe learning about social networks really helps with molecules. I don't know. Yes?
Maybe also about your nice library. Like, how good does it scale? What order?
Yeah, it's a really nice library, thank you. So I don't know, because so the thing is that we have a small team and we don't have enough manpower to fix all the little issues and to run all these experiments to figure out how it scales. So sure, especially for the higher order stuff, like doing this in terms of like trying to shoehorn it into PyTorch really has its limitations. So it's going to do better than that. But then there are the kind of downstream engineering issues, right? There's certain things have been solved in these libraries, like, I don't know, like parallelizing over multiple GPUs, and that's not going to be there already. I can tell you that the biggest pain in all of this is the batching, because for these higher, so. And the whole philosophy is that setting up one of these higher order models involves a lot of combinatorial stuff that's kind of pre-computation. So it's like finding the subgraphs in the first place, and for each pair of tensors, finding the overlapping tensors, the overlapping dimensions, and what the corresponding map should look like, and so on. That's expensive, because essentially it has to be done on the CPU side. But especially in this kind of supervised learning setting, why don't we just do all this in pre-computation, and then once it's all been done, just ship it to the GPU and say that, okay, now instantiate it for this graph, and all these data structures are already there, and the kernels can run relatively fast. The problem with this is that in the batching, you need to combine these pre-computed things into a bigger pre-computed thing on the fly. So unlike in ordinary PyTorch geometric, essentially we had to write the code for the individual graphs, and then you had to write a whole separate layer just for the batching. So the batching was confusing and very annoying to write. But for the sake of scaling, we did push through with that. Yeah. Ultimately, I'm very interested in that thing that I flashed at you, just the way that the race condition is solved. Like whether by having a different approach there, actually there is something that to be gained even for regular graphs when neural networks. Whether that's really optimal. Yeah.
So to give us enough time for lunch, which we have until 1:30, maybe let's leave it at this. Thanks a lot again.
Okay.